So I got this for one of my kids at a science museum, I don't know, 10 years ago or something. And it's pretty amazing. Now, this is the thing. There's a liquid in here. This is not water. I don't know what it is. They didn't say on the box what it is. I think it might be some kind of alcohol, but I'm not sure. And then they put in some blue food coloring so you can see it better. Okay. So, now, what is so interesting about this? You might wonder. Well, it looks really cool, but also check out, now that I'm holding it down here on the bottom, look at what is happening. The liquid is slowly rising up through the tubes. Some awesome glass blower made this. And it just keeps going. It's kind of slow, but it's consistent. So it keeps going more and more and more. And now, see this tube down at the bottom? If I don't have it tipped at the right angle, then it can't suck up anymore. It's kind of like a straw at the bottom of your cup. And then if you tip your cup, then you don't get any more of your chocolate shake, right? But, so I need to keep tipping it so that it can suck it up. All right, so what is going on here? So I'm holding this now more tightly, the bottom. So what is my hand doing? What change is happening by me holding this? What could be causing this? Because I'm not squeezing it. This is glass. So it's just by virtue of holding it. It looks like an alien hourglass. It totally does. I know. So here, let's do this experiment. I'm gonna now, with my other hand, I'm going to put the top part in my hand. And now what is happening? I'm going to close it again. Close it again. And it's empty. I emptied it out by holding onto the top part. And we can do it again. I'll hold onto the bottom part. And zoop, there it goes. All right, so why is the liquid going up when I'm holding? It's basically going away from wherever I'm holding it. It keeps going. It's funny how it pauses sometimes, like it's catching its breath or something. Okay, now it's full again. It's full up there. But I grab it and then it's like, whoop, and it goes pretty quickly back down. So we are observing expansion and contraction. So what I'm doing is I am just adding heat. And it's just enough heat, a human hand, the warmth of a human hand is just enough so that this liquid expands and is pulled up through here. So the way they've created this really cool thing, they made a bulb up here, a bulb down here, and then these are connected with the tubes in between. And they also have a vacuum. When they create this, it is not a full atmosphere of air in here. There's a slight vacuum inside of there. And so when this is warm enough, it expands and it is sucked up into this area here. That is essentially, it's got a vacuum in that area, and so it's pulling it up in there as it expands with that heat. So this is you couldn't just do this with any liquid. They specifically chose a liquid that the temperature that a hand could change the temperature, that would be just enough to be able to cause the expansion and then the movement from one side of this to the other. So I really do wonder, that's so cool, I wonder how many different liquids they tried. And I wonder how many different pressures they tried. Because it's not a perfect vacuum. You can't get a perfect vacuum. In fact, outer space is not even a perfect vacuum. So, yeah, they must have tried a lot of different things. And probably, I'm guessing they tried a lot of different shapes of these. And I have seen different shapes. So I know that different, like, when I say shapes, like it kind of swirls around a little bit differently. But generally, they look like this. And I've also seen them with different colors, like green and red and things. So there's some things that you can change pretty easily. But I think the selection of the liquid that they use, that's really the biggest challenge with creating something fun like this. So I just love this. It's a very simple contraption, really, and it's so amazing. And so that's why I got it for my child, who also thought it was amazing. And I'm pretty stoked that they still have this, that they kept it and they put it up on their shelf, and that they liked it enough to keep it around. So, all right. So I have discovered doing these ASMR videos and with my pen and with various things, but that this desk that I use is not stable, or it's tipped slightly, because look at this. Every time I put something on it that can roll, it always rolls, and it always rolls that way. So yeah. I have learned that if I'm going to do something and it can roll, then just be careful. All right. So, yeah. And let me know if you have any questions about any of these things. This is kind of like my show and tell. So, all right. Show and tell number 1, expansion of liquids. It's cool. It's a cool thing. Okay, here is my show and tell number 2. Come here. this. It's also glass, and it also has two bulbs. This is just kind of coincidental. These are just a couple cool things I have sitting around. And this one is also completely sealed and was created by a glass blower. But now, instead of having a liquid inside, this has a solid. And just like a typical hourglass, you can turn this upside down and it will fall. So I'm moving it up next to the mic so you can hear it. So I don't know if you could hear that or not, but now here's the challenge: is my mic is straight up and down. So how about if I move it so you can see a little bit better? And I'm kind of wrapped around here. I think I've trapped myself. Okay, because I want you to be able to see it better. Okay. So this is our fairly typical hourglass where you have a solid, like the grains of sand that fall through, right? Okay. So now, instead of sitting on this, this is just paper here. So instead of on this paper, I'm going to set it on this block here. And we'll do the same thing where we flip it around and have it fall. So it looks a little bit different, huh? Oh, this is so cool. Okay, I'm going to zoom in a little bit, maybe. Let's see. Can I zoom in? Yes. Okay, so, yes, it is iron sand, exactly. So, this is essentially iron ore, and that's a magnet underneath it. So all of these tiny pieces of iron are all aligned with the magnet. And now it's done. Yes, so it's quite different. And you can also, here, let me, I wish I had like 3 hands or something. Because you can move this around a little bit and it looks pretty cool. Because I just love that magnet. It's like, come here, magnet. Like, I can't barely move it off of this. It's just really... Also, you know, I just had an idea. Okay. Yeah, it just looks really funky. Okay, I'm going to try something else. We're going to have a contest. Magnet versus magnet. Because I have another magnet over here. So, let me see. I'm going to turn this sideways for a second. I know it's kind of weird, but whatever. Ooh, look at that. That's pretty good. Like, zooming in. Okay, let me grab this other magnet. I'll be right back. It's right up here. Okay. I have a couple different magnets. So I want to see, because right now that magnet at the bottom it's still attracting the iron, but now I'll show you what I'm doing here. Okay, I'm going to turn this back up like this. Okay, but I really do like that zoomed in action, so let me do that again. Okay, so you can see those like filaments, you know? Those are iron. Oh, look at that. I have a pretty good phone. I'm impressed with what it's looking like. Okay, so now I'm going to take this, can you see it? Okay, this little magnet. This is magnetite. Okay, so this is another kind of iron oxide. All right, so that is also magnetic, and I'm going to bring it in close behind and see if we can see some activity, or if that other magnet is stronger. Oh yeah, it's bringing it up. Oh yes. All right, we've got some iron has escaped. I lost the focus on there. So iron is not the only element that is magnetic. Okay, I'm going to try this. Oh, yeah. The thing about iron is that it is definitely, it has this property, and part of it has to do with the unpaired electrons that iron has, and how well they align with the magnetic field and how they respond to a magnetic field as well. This looks really cool. I don't know what you're... And by the way, if it looks like it's streaming, like it's choppy, that's actually real. Like, I'm sitting here looking at it, and the way it's behaving, it looks like a choppy stream. But it's not. It's actually like, this is what it's doing. That's so cool. It's so weird. So anyway, I really want to show you the periodic table, but I'm kind of mesmerized by this iron right now. So yeah. Okay. So as I was saying, iron is not the only magnetic element. Nickel also has some magnetic properties. And there are some lanthanides. Oh, this is interesting. Like what? Like, how close do I need to get it to do something? Like, if it's here, does it do it? Or, like, how close do I have to be? Okay, but is it going to do it there? Oh yeah, that is still close enough. That's cool. Yeah, I feel like magnetism is the closest you get to magic in science. There's just something about it. Look at that. It's so trippy. Yeah, and these magnetic fields. Okay. So there are lanthanides that are I I want this to be in better focus. Let's see, do I need to get closer? I don't know. Lanthanides that are also quite magnetic and even in some cases more magnetic than iron. So in terms of unpaired electrons, okay, I'm going to make myself stop doing this for a moment, even though I love doing it. This is a weaker magnet, yeah, okay. So this is the thing. All right, let's bring in our periodic table. All right. So get a little bit better focus. All right. So here's iron. Okay. So look at where iron is in terms of if we're going across a row on the periodic table. And let's look at potassium and calcium. Let me get a little bit closer. Okay. Potassium and calcium. All right. And we are adding in potassium has 19 electrons. Whoops, sorry. Has 19 electrons, and then calcium has 20 electrons. But the thing is these electrons are both in the s orbital, so they're paired up. And then as you begin to add electrons going across the periodic table in this way, because these are the d orbitals, they are unpaired to start. Okay, in most cases. Now there are various exceptions, and when you learn more about the intricacies of metals, then you can learn more about those. But one of the things that helps with a compound being magnetic is it having unpaired electrons. And so that's called paramagnetism, when it has unpaired electrons. And iron has that, okay, as well as this property of ferromagnetism, where the electrons align with the magnetic field. Nickel has that too, but not as strong as iron does. But okay, I want to get rid of this light reflection. Oh, I don't know. Okay. Now down here in the lanthanides, we have a similar thing. So here are the lanthanides, and what's being filled here, let's just zoom out a little bit, and when we're looking at the lanthanides and the actinides, it is the f orbitals that are being filled. And there are 7 f orbitals, which means that they can be filled 2 electrons per orbital, 14 electrons. So as you're going across, adding 1 electron at a time, these are all unpaired at this point. And so especially these that are in the middle part, they have a really large number, enormous number compared to the rest of the periodic table of unpaired electrons. So you end up with things like gadolinium that are used a lot, neodymium, promethium. A lot of these are used in devices where magnetism is needed. So actually, the smartphone that I'm using right now to do my very first phone live stream, this is kind of a test, but it's kind of not a test. I'm actually talking about stuff here. But within this device, there are some of these lanthanides that are used. And in fact, in the microphone part of the smartphone, there are some of these rare earths that are there. These lanthanides. And unfortunately, so they do have this nickname, rare earths, because they are rare. And that means that a lot of mining needs to be done in order to find them and get them and use them. And there are some countries, alas, that don't have as many rules as, in my opinion, they should, in terms of mining and things. And so it is to great detriment to some of our environment, animals, ecological systems, and things like that. But I'm also a hypocrite to say that, right? Because what am I doing? I'm using a smartphone right now. So that's kind of the conundrum that we are in every day as we make our choices of how we are going to live and the things that we're going to use, because we like our stuff, right? And we want our smartphones, but we also like the environment, and so it's hard because we don't want to say, just one or the other. We want both, right? We want it all. Okay, I'm gonna try to refocus. Can you see that? Am I zoomed out? I think I'm zoomed out. Okay. Yeah, so that's something I think about a lot. And that's actually why I'm gonna bring iron back into the picture here. That's actually why there are a lot of people who are doing research into ways that we can incorporate things like iron that are earth abundant. Earth abundant elements. This is a really nice sound if I just... Here, I'm going to bring this down. Just like spinning this around. I don't know if you can hear that. I'm going to bring the mic closer and see if you can, because it is a very nice, like, just if you can hear it, then you'll know what I'm talking about. So I'm bringing my mic, pulling my mic. Okay. See if you can hear this. So, oh my gosh, what was I saying? Oh my gosh. Yeah, there are a lot of people who are studying earth abundant elements to use them in devices and things. So, for example, silicon is one of the most... Is this in focus? Is one of the most abundant... I'm going to zoom in. Elements that there is, which is great, right? Because silicon is used in so many computer devices and other parts of technology. Silicon is used in detectors. It's a semiconductor. It's an intrinsic semiconductor. So it can be used beyond just what it's used for in computer chips and things like that. And phosphorus is also fairly, relatively abundant, and it can also be incorporated into semiconductors to give it different properties. And so if we can, as much as possible, use things like oxygen's another one. Oxygen, very abundant on planet Earth. Silicon, phosphorus, and relatively speaking, I'm gonna move this so I can, in fact, I think I'll move our hourglass over for a second. Oh my goodness, I'm sorry. That was loud. That was the iron in the hourglass attracting the base metal, and they snapped together really loud. Okay, that's what that was. Okay, so we've got iron is extremely, relatively abundant on planet Earth. So is titanium, relatively speaking. Aluminum as well. So if we can instead use those elements that are more abundant, then we will not have to go mining and trying to get trace amounts of gadolinium that we might need to, tear apart the entire side of a mountain or something just to get a tiny bit of gadolinium so that we can make our devices. If perhaps instead we could be clever and try to find ways that maybe mixing cobalt with nickel into a compound and doing something that is almost as good as what gadolinium makes or something, then we can have it all. Like I was saying, we can have those devices we want, or if there's materials we want, but not at the expense of taking away the environment from some of our cohabitants on planet Earth, some of the animals, plants, other creatures that we are stewards of, right? So, I love talking about that. What's in the center of Earth? I talked about iron being relatively abundant. Oh, so sorry. I need to be better at reading the chat. So I know, isn't that funny? The iron looks like a hedgehog, and then yeah, cobalt. So some of these metals, they do have these magnetic properties, but they're just not as well known for having them because iron has such stronger ferromagnetic properties. But yeah, there are quite a few elements. I should look up what they are, the ones that are the most magnetic. That I feel like that's something I should know. Yeah. Now, iron. Iron is at the core of planet Earth, right? That's something that we're told, and we see pictures of kind of like a cutaway, as if you were cutting into an orange or something, and you can see all the layers of planet Earth, and and we see that it's got this iron core, and there are parts of it that are in the middle, the center of Earth. It's very dense, and so it's a solid iron core. And then it's liquid, and then of course we have all the stuff where lava comes out, right? Have you ever wondered why? Why iron? Why iron? Why isn't it manganese or cobalt or something like that that's at the center of Earth? So I need to grab something, so I'm going to let you ponder that for a minute. That's my question. Okay. I am back. So, what do you think? Why iron? Why iron? Well, we have to delve into the realm of nuclear physics, nuclear chemistry, and it has to do with the stability of the nucleus of iron. And so iron is the most, and actually there is an isotope of nickel as well, but these two have the most stable nuclei. Hydrogen is less stable. So hydrogen is element 1. It's got 1 proton. That's it. That is the least, well, it's not, is it the least stable? Yeah, in terms of binding energy, hydrogen is the least stable, and that it increases pretty swiftly as you, hang on. Okay. As you get to helium, and it gets more stable as you go across the rows, and then it has the strongest binding energy, or in other words, this most stable nucleus is iron. Okay, and then it decreases, the stability decreases, and it trails off and is less stable for things like uranium. Okay, uranium, plutonium, these are well known as being used in nuclear fission processes where you're breaking things apart. All right. And when you break them apart, the nuclei become more stable. In fusion, like in the sun, hydrogen is fusing together with another hydrogen or with a helium, and it's making something bigger. And that is also becoming more stable. So that's because those hydrogen and uranium are on the extreme ends. They are on either side of the most stable nucleus of iron. So whether it's fusion or whether it's fission, either way, you're going to get energy out. So with stars, there's energy coming out, and with our nuclear power plants, there's energy coming out. So either way. And so iron being the most stable, it makes sense that there are a lot of planets in the universe that have iron, a lot of iron in them. There are a lot of asteroids in the universe with iron. And when you get to the point of where a star is nearing death, that also has a lot of iron in it. Because the star has been undergoing fusion for a long time. And there isn't any hydrogen left to keep undergoing fusion, because it's making bigger and bigger elements as it undergoes fusion. And then once it gets to iron, it can't create energy anymore, and the star dies. So that's when we get a supernova and a black hole and all that good stuff. So, alright, so yeah, you never thought about why iron? Yeah. Yes. Okay, sorry. You probably, Dexterity, you probably typed up all this before I said it, so, yeah. Oh, the red color, that's a good question. Yeah. So, yeah, I will look into that, and in fact, I definitely want to very soon set up a conversation with an astrophysicist coworker, a colleague of mine, Rick Watkins. He got his PhD in astrophysics, and he still does work on that, and that would be a really good question for him. I'm really curious, and I want to look it up, but he would be a great person to talk to about that. So, yeah, very cool. All right, let's see. What else do we have? Oh, I wanted to show you my calculator. I was thinking, like, hey, we haven't done any calculations in a while, and so here's my calculator. I love it when it does this. I don't know what that means, but it's funny. It's sort of like, it makes me think of Star Wars and Star Trek and stuff, where they're trying to show like alien notifications on the a spaceship or something, and yeah, anyway. Okay. Yeah, should we calculate something? I don't know. Let's see. I'm gonna zoom back out. Oh, is that? Oh, maybe this. I'm like, why is this dirty? This must be from the iron or something. Alright. So, what else do I have up my sleeve? I think that is, yeah, in terms of show and tell, that's what I got. So, yeah, let me know if you have any questions. Trying to think if there's a yeah, no. All right. So I think I'm gonna end here. Whoa. I'm gonna end here pretty soon. I was gonna see if I could get it to like slowly come over, but no, It's like once it gets close enough, it just pulls. It just pulls. Yeah, no, I can't get it to move slowly. All right. Well, I am going to wrap it up here. But do let me know. You know what's cool about this? And I might bring the phone back down because I wanted to say something else about the iron. Okay. So this is the iron when there is no magnet. Okay, I am going to focus, don't worry. Okay. So when there's no magnet present, it just looks kind of like, it looks kind of like sand, I guess. Am I too close? So hopefully you can see that. Oh yeah, wow, that's pretty good. How's that focus? Yeah, there's just tiny little spheres. Tiny little spheres of iron. Okay. So now, let's look at how it differs when it's on the magnet. So, exact same thing here. It's probably, oh God, I was going to warn you, I'm sorry. And right now, we don't see much of a change, right? It's ever so slight, but they still look, like spheres, right? Okay. So, if we were able to look at the ones on the bottom that were closest to that magnet, it would probably look different. It would probably look more like this, okay, where these pieces of iron, let's zoom in again, where they are, oh wow, sorry, I don't know why it did that, where the pieces of iron are lining up with the magnetic field. And then once the magnetized iron that's next to the magnet, it gets magnetized, so then the pieces of iron that fall on top of that can then easily get more magnetized. And then it just follows. They just pile up. They pile up. They pile up. So this is the same iron that we saw before. It's the same amount. It's the exact same iron. But now we see this lump. Instead of laying flat, it's the hedgehog. Right? And you can even see, like in the shadow, you can see how it's kind of spiny, right? And yeah, that's just because of this magnetism that is transferred from the iron close to the magnet and then it passes it along. Essentially, they're tiny little magnets now. And so they magnetize each other. All right. Very cool. Yeah. Awesome. Well, let me know if you have any last questions. I'm gonna go over and out now. And I hope you're having a good morning, good evening, good afternoon, wherever you are. I am gonna show you one last thing. Let's see, I'm gonna have to zoom. Okay. one last thing over here. So where I am, it is, what time is it? It's midnight. And Neil knows that it's midnight. He's like, why are you out here? Why is the light still on? And yeah, so he's fast asleep, and I will probably be fast asleep soon as well. Alright, well, just like with iron filings, I think I could stare at Neil for a long time as well. So, alright, I'll bring it back here, and thank you for joining me. Put it back on the hedgehog. Thank you so much, and I will see you next time. I will be streaming for sure. I mean, maybe before then, but for sure on Sunday, my time, Pacific time, Sunday at 5 p.m. And it is on my schedule on my channel, so you can check that out. And hopefully I will see you then. And now I get to figure out, how do you stop streaming on your phone? Because I have not done this. Okay. Maybe it's here. Alright.